In this video, we're just going to be going over some examples of hypothesis testing. For the first example, we're going to do a large sample test. So for our null hypothesis, we have mu is equal to 25, and our alternative hypothesis, we have mu is not equal to 25. So at that point, we know it's a two-sided test. And then we get alpha is equal to 0.05. So we know we can create our z-value. So we can create z of alpha over 2 is equal to z of alpha, 0.05 divided by 2, so 0.025. And if we look that up in our z table, we get that z of 0.025 is equal to 1.960. And then we can look at our n and sigma, and then our x bar, and x bar is 25.41. So to create our z statistic, we have z is equal to, we have x bar minus mu over our sigma value divided by the square root of n. And if we fill in all those values, we have x bar is 25.41, so we have 25.41 minus mu was 25 for our hypothesis test, so we can put in 25. Divide that by our sigma value, so 2, divided by the square root of n, so square root of 100. And we get that 25.41 minus 25, so we get 0.41 over 2 divided by the square root of n. Square root of n, so we get square root of 100 is 10, so 2 divided by 10 is just 0.2, so we get 0.2. We divide 0.41 divided by 2, and we get 2.05. So at that point, we have our z is equal to 2.05. And 2.05 is greater than that 1.960, so greater than 1.960, which is equal to our z of alpha over 2. So at that point, since it's greater than that value, we can reject our null hypothesis. So we reject H naught and accept our alternative hypothesis, or HA. So at that point, we're saying that we think that the mu is not equal to 25. For our second example, we're again going to do a large sample test. So our null hypothesis in this one is mu is equal to 0.25. And our alternative hypothesis is that mu is greater than 0.25. So at that point, because our alternative is mu is greater than 0.25, we know it's a one-sided test. We have our alpha is equal to 0.1, n is equal to 50, sigma is 0.05, and x bar is 0.2578. So since we know our alpha level, and it's a one-sided test, we're just trying to find our z of alpha, and that is equal to z of 0.1. If we look that up in our z table, we get that is equal to 1.28 and about 2, we'll say, to give us a little bit of margin of error. So again, here we're interpolating on our z table, trying to figure out the in-between value there. We're just going to round it up to 1.282. And then for our statistic, we calculate again our z value, and that's equal to x bar minus mu divided by our sigma over the square root of n, and we get x bar is 0.2578 minus our mu of 0.25, and that's divided by our sigma of 0.05 divided by the square root of n, which is 50, and that comes out to be 0.2578 minus 0.25 is we just get 0.0078, and 0.05 divided by the square root of 50 is equal to 0.007071. If we divide that out, we get the value of 1.103. So for our test, we have z is equal to 1.103, which is less than 1.282, which is equal to our z of alpha. So at that point, we have 1.103 is less than our z sub alpha, but our test is for mu is greater than that 0.25, so that means that it is not greater than, so we fail to reject our null hypothesis. For our last example, we're going to do another hypothesis test. where our null hypothesis is mu is equal to 100. Our alternative hypothesis is that mu is less than 100. So again, we know that's a one-sided test. We have our alpha is equal to 0.05, n is equal to 15, so that means we're doing a small sample test. So that means we're going to be using our t statistic instead of our z statistic. We have our s value, or our sample standard deviation, is equal to 20, and our x bar is equal to 90.5. So again, we'll first calculate our t statistic now. So that's t of alpha, and that's equal to t of alpha is 0.05, so we have 0.05. And if we look that up in our t-table with n is equal to 15, so that means our degrees of freedom is equal to 14, 15 minus 1. So t of 0.05 with 14 degrees of freedom, we get 1.761. So again, we can calculate our statistic. Our test statistic is t is equal to, we have our x bar minus mu divided by our standard deviation. So now we're using s divided by the square root of n. So we get x bar is 90.5 minus our mean of 100 divided by s, which is 20, over the square root of n, and n is equal to 15. So that gives us 90.5 minus 100, we get negative 9.5 divided by 20 divided by the square root of 15 is equal to 5.164. We divide that out, we get negative 1.8397. And now we're going to compare. So we have our t value is equal to negative 1.8397, which is less than negative 1.761, because negative 1.761 is equal to our negative t sub alpha. So again, it depends on our test. We're doing mu is less than 100. So that means our t value for our comparison is that negative t sub alpha. Since t sub alpha is equal to 1.761, we use our negative 1.761. So since t is less than that value, we're doing a less than test. We reject our null hypothesis and accept our alternative hypothesis, so HA.